Good evening, everybody, and welcome to N-Simplex Pachinko. This is Obi-Wan Pez. Sorry for the late start here. We had some stuff going on, and I apparently just put the wrong category in. So, oops. So Megalomorph with that. I'm even afraid that I don't necessarily know the term simplical complex. Is that the... It has been a long time. Never took who's it? Topology. So Simplicial. There we go. Hey, Super Brain. Doing all right? What am I even looking at? Good lord. Okay, but no limitation as far as what you get after that, as long as you then have only that number of dimensions. I mean, there might be some limitations, I guess, but... Alright, well, let's just see real quick, make sure... Yeah, right. Somehow... Alright, so... I am probably, hence the name of this particular stream, probably not going to be doing tensor calc for a little bit, just so that I can either get my skills up or get a bit further. And besides that, it's also kind of it's an interesting exercise in watching Obi struggle. But, I mean, they probably exist somewhere. I didn't turn the music up. Oh well. Well, yeah, I meant that you could go with a, adding two simplices to a tetrahedron or something like that, but it's going to either exist in a space or in a lower dimensional environment. It's not going to extend into any higher dimensions once you've established what dimension it is. Oh goodness, don't start that already. Alright, so... Which, it's all well and good to talk about simplicial complexes, but at the same time, it just wouldn't match my name. All right. Okay. It's funny, you can't edit the name for this thing here. You have to go back to the main menu. Weird. Alright, so I pulled the book we're talking about here. This is Mathematical Thinking and Problem Solving. Mathematical Thinking, Problem Solving Improves, second edition. I believe this is one that my spouse had for her proofs class. I think. I figured we'd start on something potentially a little bit easier than the tensor calc book, which, I mean, it's fun and all, but at the same time, I'm muddling through half of it, so this would be a little bit better for everybody, I think, and probably a little more within reach of anybody who's just meandering on through this channel. And hello, by the way, to anybody else who's here. I have no idea. Is that YouTube or also Twitch? I'm seeing topics and combinatorics. Let's see, section 1.5. This book does not appear to be broken up into sections like that, so... Oh, okay. It looks like there's only about a year of videos on his thing here. Thinking about math problems in real time. That could potentially be it. So let me... Video in which I fail to solve problems about invariance. Nice. Well, that's rather embarrassing. Nah, it's fine. I don't really follow anybody else's, math lectures anyway. I mean, apart from going to yours and occasionally Tayo's. Oh, last 2 weeks, okay. Okay. He's been on a lot of stuff. Okay, well, I mean, good news, right, is that I've got the entire book and however long I feel like doing it. So, oops. Don't you hate it when you're a Fields medalist and you just can't get something? And somebody comes along. Oh, man. Some guy. Alright, so the first section of this book deals with a quadratic formula, and that is not a writing implement. That is... Oh, man. You all see what I did there? Yeah, that's where we're starting from today. All right. So the first section talks about the quadratic formula, and specifically they were talking about the ancient Babylonians were trying to find some system of trying to find the or given sum and product find the given two numbers. So we know how to do that these days. Back in those days, they didn't have a whole lot of information about that, and especially didn't have, algebra, which was some 3,000 years later, and not from Assyria. And I left all of my who's it? Cuneiform stuff at school. If you ever get the chance, watch pretty much anything you can find from Irving Finkel. He's hilarious. I love him. This guy with a huge white beard that like eats his face, big ponytail, and thick glasses, and he played uh, the Royal Game of with Tom Scott. And I think he said he translated the rules from the Royal Game, or maybe it was the guy from like 1900. But either way, he learned because of all of this stuff. It was just crazy. Yeah, there's also in Elite Dangerous, you can also buy a spoiler kit for your. It makes me laugh just saying it. You can buy a spoiler kit for your spaceship. It literally has no effect on the entire ship. It just entirely cosmetic. I mean, clearly. Clearly. uh, Terrible. So anyway. So they're saying, alright, so to find a sum x, or sum s, we can call that our two numbers x plus y. And to find some product p, we can get that as x times y. This is the product of those same two numbers. Yes, go faster stripes. You need go faster stripes. Yeah, I think he might have a slight smaller attitude. Aphelion! Welcome, good evening. Yes, you should always buy the stripes. Panda is one of our resident pilots, I believe, yeah? And do you... Silly of me to ask this now, because it's been so long, but is it aphelion or aphelion? And follow-up question, is that British? Oh, that's true. Yeah. Right. Well, just to make sure I never mispronounce it correctly. Yes, definitely aphelion. Oh, yeah, that's fair. Man, I just did like silly math research to get my name. I guess the other name was because of this. Yeah, one of my friends was walking through a store and like stopped and kind of turned, and then there was an entire wall of me just staring back at her, and she's like, "Duh, did you?" She said she had to buy one. It is no longer mint in box because I needed to eat the candy one day. Um, all right, so anyway. I promise I'm going to actually get to some actual problems at some point. It's just, you know. I was 27 and I was hungry. Alright, so with x equals, you bring the y to the other side, and over here we can replace this x with s minus y times y. It's going to be equal to our product, which is then going to be a negative y squared times an sy is equal to p. And move all this over to the other side. We're going to get here a 0 is equal to y squared minus sy plus p. So in our, modern mathematical world, we can pull this off and say, This is a quadratic, and all of the quadratics of the Babylonians would have had positive numbers in for the values of s and p, and therefore all of their quadratics would have looked something like this. Not, again, that they had algebra to do it, because that didn't come for another several thousand years. Yeah, I mean, probably Obi-Wan was taken, but I didn't even try, because I was like, I need a name that's at least like somewhat unique-ish. And that was when I first made my Twitch account, probably, I don't know, 5 years ago? 6? Whatever it was. Oh, it was 2016, maybe before that, but right around 2016 when Alpha came out. Project Alpha from Geek and Sundry. I needed a new username, and I was like, ugh. So Obi-Wan Pez worked very nicely. Oh man. Yeah, I think I had that problem like a couple of years before trying to come up with something else, and then I was like, nope, F it. So I just made like, because I had my name from before, and then I had like several other accounts that I had to create because that one was taken because somebody with the two initials after my name, you know, like first name. I For me it was because I used to do a particular activity and it could be cut down to two letters. So I was like, okay, I'll just put my first name and then the activity abbreviation. And then everybody was like, oh, I need to have that because it's my first name and then middle and last initial. And I'm like, fine. Yes, but you've you've done the accidental puzzle hunt. So I left a lot of my privacy settings open, and Superbrain here was able to figure out because Superbrain um, was able to figure out all of my credentials. I was like, and it was that day I was like, oh, shut her down. Made everything private as much as I could. I'm sure some of it's still there, and you could probably figure out a whole bunch of stuff, but why, thank you. Ish. Ah, white hat, I see. Oh, I see. All right. So then generally, they decide, all right, let's try to figure out here. I mean, like, I still try to use Facebook when I need to communicate with, like, my family. Yep. That's about it. So without loss of generality, we could take negative AS to be equal to some arbitrary, well, not arbitrary, but some other value B, and AP to be equal to C. And then therefore we get the same standard quadratic formula that we're all used to. Except people complain I'm using y instead of x. Oh, whatever. Okay, so then with this we can do the quadratic formula thing. So um, several different ways to do it. Let's see. Usually, I usually like to come at this from my other stance, where I do the function transformation. Yeah. So if we do this, we end up with y equals a times f times. In this particular case, well, because it's a... Come on. Really? Jeez. Because it's quadratic, we can go like this. Nope. Squared plus d. We could say here that we have a times, this is b squared times x minus c squared plus d. Oh. Wait, what? This thing? What are you looking at? Yeah, okay. That's fair. Did you find that already? Alright, ab squared can be arbitrarily renamed to just a because it's the constant that's being multiplied out front. Because that's a new picture. I'm pretty sure that's not even public. Alright, so we get x minus c squared plus d. But if we want to keep this distinct from this stuff, because this c is not equal to that c, and that b was not equal to this b, so the a is going to be the same. Once you get it all knocked out, then it's the same. No, I get what you mean. Like this is like a 0 and this is a 1 or whatever. But so if we make this intentionally different than what we have down here, and this is going to be x minus, a lot of people call this h squared plus k. Any idea why we use h and k? Because I have no idea. I'm imagining it belongs to, I don't know. Is it the Germans? So if we want this to be in this form, okay, or at least not 100% directly. So if we want this all multiplied out to see what the relationship is between this thing here and this thing here, it's going to be a times the quantity, x squared minus 2hx plus h squared plus k, y equals a x squared minus 2ahx plus a h squared plus k. I know I did this like last year or whatever, but why not? So y is equal to a x squared yep, minus 2ahx plus ah squared plus k. So if we want to relate these things together, we have here the same constants in this one, which again can be rewritten as y equals ax squared plus bx plus c. Can relate the constants together. A equals a, so that's easy enough. B equals negative 2ah. And c equals ah squared plus k. Which, if we then want to solve for the variables we don't know, so h is going to be equal to b divided by negative 2a. Oh, that seems familiar. And k is equal to c minus ah squared, h being this thing here. So c minus a times b over negative 2a. Our a's are going to divide out. Our negatives are going to divide out. And so we're left with c plus... Oh, that's squared. Shoot. Man. Now, I can do that, I suppose. That squared. Okay, save myself. Equals c minus a times b squared over positive 4a squared. Alright, that a can divide out one of these a's here. So we get k is equal to c minus b squared over 4a. Or, put a 4a on top and bottom. We get a 4ac minus b squared all over 4a. Okay, so this is how these relate. You can use them basically however you want. But my favorite thing to do with this is to say, okay, this is going to be the way to break all this down and relate all this stuff. And then the quadratic formula for this is you're going to solve this equation in its that form. Set this equal to 0. That y equal to 0. So 0 equals a times x minus h parentheses squared plus k negative k comes over, divides by a, and we get x minus h parentheses squared. Take the square root of both sides, and we get the absolute value of x minus h is equal to the square root of negative k over a. And then this implies that we need, again, both the plus and the minus. Since this is an equation, we don't have to consider like which direction it's moving in and all that stuff. It's just we have the particular values we need. If you want to see this otherwise, this is also, at least I find it kind of helpful. I don't know. You have your quadratic looks something like this. We have our x-axis looks something like this. And we have our zeros here and here. And we have our vertex, which translates or has a projection onto the x-axis here. So the fun part of all this is that this is where x equals h. And then all this stuff here and all this stuff here is just the distance, which absolute value is distance. The distance between x and h is going to be all this stuff. So these two things are going to be the positive square root of, let's just zoom in on this because it's totally going to work. Nice. This is the square root of negative k over a, and then this is the negative square root of negative k over a. We're totally going to be able to read that out at 100%. It's fine. There we go. So here we get x minus h is equal to the plus or minus square root of negative k over a. And so therefore x is equal to h plus or minus square root negative k over a. Now I think I might be the only teacher who actually teaches this to my pre-calc classes. But like, this is so much easier. I need to get my thoughts properly organized on this because I'm doing it on Friday. I mean, I've done it every other year for the last like 3, but or every semester for the last 3 to 6, somewhere in there. It was probably before we went virtual the first time. Oh, it's been that long. All right. So then this is going to help us find this thing out, because now we can say, okay, y is going to be equal to h plus or minus square root of negative k over a, where h is equal to negative b over 2a plus or minus square root negative k is this thing 4ac minus b squared over 4a divided by a. It's going to make that a squared. Negative b over 2a plus or minus square root of the top. So that's going to be a positive b squared minus 4ac. And then we're going to divide by a square root of 4a squared. Why, hello, 2 curbs. I actually do not have a queue set up. I meant to ask Megalomorph about that. Or maybe I already did and got an answer on Discord, but whatever, it's cool. Over 2a. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah, this is the non-completing the square version of the quadratic formula, which you do kind of have to know what the function transformation form is, but okay, that's kind of where I come at from my entire class. So if my students don't know that, they're in a lot of trouble. What would you like tonight? So y equals this big thing, which we know is the quadratic formula. K points. Ah, man. D-dimensional hypersphere. Not it. Interesting. Change background to blue. Angle between each point and its closest neighbor to be as big as possible. So minimize the distance between, well, I guess absolute value, but anyway. um, such that it's not really how we use this, but whatever, it's cool. I did some pseudo notation for my um, uh, pre-calc class today, and they were just like, "What are you doing?" This is almost how we use this notation. Just don't worry about it. It's fine. And put the translations next to all of them. Yeah, we don't actually want this such that, but anyway. Okay, find the minimum xi minus xj, and then find the maximum of the angle between them. So, all right, so in order to find the angle between them, and that's a d-dimensional absolute value. Hope it's not your homework. So the angle between two things. So if you're thinking like in 2 dimensions, you're looking at 2 points that are on a circle, and you want to get the maximum angle that's between them this way. And in 3, something here and something, back into the board, you can draw a plane through them, and the angle that is on that plane, right, from the origin on that plane, is then going to be some theta or whatever. Yeah, I just don't remember all of the notation for it because it has been literally that long. Uh, mm. And my engineering math book is under my monitor over here, so that doesn't help. Yeah, it's been like 10 for me. So. All right, to calculate the angle between two vectors, use a dot product. I was thinking there was something about that, but okay, so take the angle. Theta is going to be equal to arc cosine of, in 3 dimensions, this is x1 times x2 plus y1 times y2 plus z1 times z2 over, whoops, dependent upon the norm of the space. Yeah. Square root of, this is the distance, right? It's the norm of vector 1 times the norm of vector 2. Yeah, so like in huh. Yeah. So I mean, technically, right? This is in any number of dimensions. We could make this work as um, so if we're only doing two vectors, right? Oh, right. This would be 1, 1, and 2, 1 plus x. Oh, I'm hating myself for this already. 1, 2, x 2, 2 plus out 2 x 1 d x 2 d out to here we get the norm x1 1 squared plus x2 no, 1 2 squared plus x1 3 squared plus all the way out to x1d squared times the square root of x2 1 squared plus x2 2 squared plus out to x 2d squared. Okay, so again, there's only two vectors, so we can just do this. This is fine. No, not plus. Jeez. So when you define pi as the ratio between the circumference and diameter, All right, so who wanted their calculus to be infinite dimensional? Potentially. It might be a little awkward with a vector. Man, how do you even do this? Oh, believe me, we'll find it somewhere. All right, so on 2 dimensions, right, if we assume that the first one's going to be at 0, again, without loss of generality, we can say pick anywhere on the circle. So the 1 point is just by itself. 2 points, that's going to get a point directly opposite it. 3 points. Wait a minute. Right, this is just going to... Hang on. Right, so this is just splitting up our 360 degrees over one thing. Oh man, did you watch him play with the Witness? Oh, that was a little messed up. um, what was it? Baba Is You was also a funny one. He and his he and the guy he's working with are trying to figure out like the rules of the game. It's a giant word puzzle. They're good for it. Right, so on this particular case, let me go back to the where you said this. You want the angle between each point and its closest neighbor to be as big as possible. So, I mean, are we doing this as magnets, essentially? Sorry, I don't know the other guy's name. Mark, okay. So, Curbs, is it going to be... Yeah, I mean, do you think that the optimal solution is just going to be spreading them out as far as they can go? So that in the case of just a circle, they're evenly spaced around the circle. So then on a sphere, they would be as spaced out as possible. I mean, even in 3 dimensions, it's not that hard. It's a little awkward, but they've worked out the... I mean, probably. I'm just working my way up. So, like, I just want to know if I'm stating the problem correctly-ish, so that, like, again, on a 2 or 3-dimensional figure, then we would be looking at trying to spread out all of the points as evenly as possible. Okay. Well, yeah, I mean, 12 and 20, we have literal dice that are that are our models for this. So all the other cases, we don't quite have them. I mean, not that we don't have them, but we may not have nice solutions for that. I don't know either. I mean, yeah. Is that a cylinder? So yeah, it seems like we've potentially got like classes that we can get, which will at least have um, simple answers to it, or at least certain values. Hmm. So if it's sorry, if we've hmm. Yeah, it sounds kind of like a centrifuge problem. Being somebody who's played around with Fold It, oftentimes I think of it as, you know, having magnets on something and then giving it a good shake and seeing them all rearrange themselves. But yeah, I think you're definitely right in the sense that you're not going to have a nice, unique solution for any of those ones that are in between, or at least not many of them, or at least it won't be necessarily clear that there is a clear solution. think I agree with both of you on that one. Yeah, well, I mean, on a sphere, it's not difficult because, right, these two will automatically go to the farthest points that they can. And then I think if you try to put a third on, they're going to stay in a plane. This will jump back here. And so their central angle out to each of them is going to be 120. And then the second you try to add a fourth, that's what's going to make this jump to become a tetrahedron. I should not move that one. Alright, keep one of them the same. Alright, so then it's going to jump to like... That's totally a tetrahedron. Right, and that's the thing, Super Bright. I think that this is going to be almost an equivalent problem to figuring out configurations of electron clouds. Although in this particular case, they're all going to be on like the outer shell. Oops. Yes, well. Yeah, so we're not going to have any more until we get 8, and then we get a nice cube. Or you're going to get a bunch that are potentially movable. Until we get out to 8, and then we get the cube. And then 12 we get the tetrahedron, and 20 we get the icosahedron. And the rest of them, who knows? You know, like the properties of L1 and L2 norms in high dimensional space? Is there any particular properties that these have? That's familiar. Yeah, Super Mario World. I mean, the minimal angle is going to be um, infinitesimal, but but if you want to actually make it, um, again, pretending that it's an electron cloud, yeah. How do we figure out the angles that are going from the center? To each of those things. So yeah, it is. But I mean the angles between um, angles between vertices of a tetrahedron. I think it might. Tetrahedron's 109.5. With 3, that's going to be 120. Oh, 6 points is an octahedron. Right, I forgot that one. Okay, so it seems like a lot of this is belonging to a Thomson problem. It's a class of problems proposed by J.J. Thomson, who was trying to work on the atomic model. And they're talking about the minimum electrostatic potential energy of a configuration of n electrons. So I think that's going to give you the thing you're looking for. Quite possibly. Looks like 5 electrons gives a triangular dipyramid, where you put an equilateral triangle along the equator and mark each of the 2 poles. So it's basically 2 tetrahedra stacked on top of each other. That's interesting. All right, hang on a minute. Is it squished a bit? Or are they not on the poles? Oh, yeah, okay. I was just thinking like all the radii are going to be the same. So. Oh, that's good. Right, so n equals 5. 1. That was a bad idea. Two, 3, 4, 5. So then where are the closest points on this? This is going to be... Ooh, this one actually is a little bit more interesting then. Because these three lie on a great circle. But then this one is up at the top and this one's down at the bottom. So that's like cutting through. So like this one's 90. This one here is going to be 120. And then the one that goes from this point here to this point here is going to be 180, but that's too long, right? It's 2r between the points, so that's clearly out. But then we've got, between these 2 points, we've got an R and an R and a 120 degree angle. And between this one and that one, we've got R and R and a 90 degree angle. Okay, so that's, yeah, that's the least. That has the least distance between those 2 points. So that's going to be just square root of 2r. R root 2. Whereas the 120 degree angle that's right, isn't it? Because we're going from the center out to each of these points. So that's how that's working. And you've got RR and a 120 degree angle. Yeah. I mean, in this case it is. In theory, at some point, there could be... I mean, they've all got R's. Yeah, never mind. Okay. Yes, fair. Ayo. Alright, so 90 degrees is going to be the minimal angle that you can then maximize. Or 90-degree angle gets you the minimum distance, which then you only have one angle. It's deterministic. Right. So then 6 gets you the octahedron. In 3 dimensions, it might not be that bad. When we've got numbers that we're actually using that make some sort of sense. Is this another one? Is this just another like 4 on the equator and 2 at the poles? Or is that not? No, because the sides have to be equal this time. At least I think they are. Nope, that's a cube. Got so many freaking D20s in here. Occasionally. Not anytime recently, but yeah. Once upon a time I did a Titan's Grave campaign. And then I really, really, really want to play Vast, but I don't have the rules. And Jackson Lansing won't give them out to people because, you know, it's tied up in, like, copyright and stuff. I mean, not that I would want... I would pay him, but the problem is that Legendary Entertainment would want their cut. Okay. So these are square pyramids. They're all equidistant from the center. I mean, that's got to be it, right? Oops. Ah. Okay, so that's 9 degrees. That's literally everything is 90 degrees. So again, with n equals 4, this is a platonic solid. N equals 6 is a platonic solid. N equals 3, well, that one's just given by the fact that it's nature. Right, we're stuck on a plane. So n equals 8. It's going to be our... Oops. Cube. It was also 90 degrees. Oh no. Because if you draw any plane, right, if you draw any plane, it's going to cut through 4 of them. Or like draw the plane through the diagonal. The closest points are going to be along an edge. Yeah, and there's 4 triangles going all the way around, which are then... No, they're not equal. Might be 90, but I don't know. I don't think it is, because the angle I'm drawing off of that, the plane that I'm drawing that's cutting through the middle, right, has to go diagonal. So if the plane's going diagonal, that means we're going to average out. It's still going to average to 90, but... Okay. Here we go. So if each of these are R, okay. Center, middle. So the middle is going to be, well, we'll just call it 0, 0, 0, 0, right? 0, 0, 0. And then each of the corners is going to be, it's the radius out, but we're trying to figure out the angle. So, Alright, so the outer diagonal here is the radius. And then we have a vertical diagonal along here. Oh, it's half. Oh. So that makes it 3690. So this has to be... No, wait, hang on. I'm just getting too excited. It's fine. Okay. No problem, Gerbs. We're making weird sorts of... Yeah. We're making weird sorts of progress here. No problem. Okay. So from the center... optical illusion. Okay. So we drop this down to the center. Totally the center. This is going to be 1/2 a side length. And then this here to the center. Okay, so we could draw all 4 of these going this way. This is going to be a right angle. And each of those are going to be 1/2 √2 times the side length. Right? Probably. Right? Because if this is the side length here, S, then each of these things is √2/2 times that, or 1/√2 times S. So √2/2 times S. Alright, so that means we now can figure out that what R is in terms of S. So this is R. We get 1/2 S squared plus, let's just do 1/√2 S squared is equal to R squared. So this is going to be 1/4 S squared plus 1/2 S squared. So that's going to be 3/4 S squared is R squared. So R equals √3/2 times S. That is a suspicious looking number. So if we build in this R over here, now we get an isosceles triangle going to the outside. This is the angle we want. So we can do law of cosines. I mean, I guess we could do law of sines. Doesn't much matter. So sine of theta over S is going to be equal to sine of minus theta over 2 over root 3 over 2s. I'm sure this is fine. I'm sure it's fine. Is there any other way to do this geometry? Alright. Shouldn't be too bad, actually. Okay, so this is going to be root 3 over 2 sine of theta. It's going to be equal to, s's are going to go away, and we're just left with this. So I like the fact that that kind of goes away. Theta over 2. Right, now this is why we learn trig identities. So if that's that, it's going to be first quadrant, so we only have positives. 1 minus cosine of 180 degrees minus theta all over 2. Cosine of 180 degrees minus theta is just negative that. So that should be a positive cosine of theta then. Check me on that. Let's do... No, there it is. Had it open the whole time. Okay, so this was negative cosine 180. Ugh. Right, you want this in radians. Minus theta. Over 2. Nope. Oh no, I don't want the over 2 part. Oh. Yep. Okay. Those are equivalent, so cool. That makes it a bit easier to solve. Especially since root 3 over 2 sine of theta, we can square both sides. Get this thing out of the square root. This is going to be 3/4 sine squared theta equals 1 plus cosine theta all over 2. Multiply both sides by 4. We get 3 sine squared theta equals 2 plus 2 cosine theta. Change 3 parentheses 1 minus cosine squared theta. This is why I do trig, folks. And then we're going to move this over to that side. So 0 equals 3 cosine squared theta minus 3 plus 2 cosine theta. And 3 cosine squared theta plus 2 cosine theta minus 1. Oh, that's lovely. There's an answer. And it doesn't look like I think there's one answer, and it's not difficult. Maybe. We'll see how it goes. So this is going to be 3. Right, hang on. Cosine squared theta plus 3 cosine theta minus cosine theta minus 1. Okay. Well. 3 cosine theta times cosine theta plus, nope, 1 minus parentheses cosine theta plus 1. So cosine theta plus 1 is going to get us a negative answer. Well, okay, it's not going to get us a negative answer. It's going to be -1, which gets us 180 degrees. So we're going to eliminate that one. The other is 3 cosine theta minus 1, which again, we set this equal to 0. This is going to be theta equals the inverse cosine of positive 1/3. That's a much nicer number. Calculator. In degrees, negative cosine of 1/3, 70.52. Five three. Yeah. So the dodecahedron's not going to do it, because this has too many things going on with it. But the dodecahedron definitely does. Yeah, we can figure that out. Of course, somebody has all this information online, so we're just doing it for fun. Ah. Mm-hmm. I mean, it's just a matter of uh, um, anyway. And so if they're doing this, so if you put an equilateral triangle attached to every single face on the dodecahedron, you get a decahedron, right? Well, it does say that there is a. Oops. Nope. Hang on. What's going on there? Yeah. There's an unsolved problem regarding the icosahedron and dodecahedron and their circumscribed spheres. Close. Uh. Whew. I haven't made that one happen in my class yet, so been lucky. Oh, it was great. I had a ninth grade history professor who went on just with. I mean, he lived up the street from me, so he was uh, like I knew him, and his son went to school with my brother. It's like we're always sort of hanging out ish. He was 2 years, or yeah, they were 2 years back in school, so it wasn't like we were actually hanging out, but I know who he is. We were in scouts together, all that stuff. So we get to high school, and the father is the um, ninth grade world history professor, and he goes on and on about all sorts of stuff just in class, and he makes these like tangential connections which none of us get. We're ninth graders, right? Even when we take the best notes that we possibly can, it just makes absolutely no sense. And so uh, we dub them his name isms. So but he would talk about you know, the grand cathedrals and the churches that would have the flying buttresses on the outside, and the people would be kneeling on the inside and having their eyes to the top of the ceiling, and we're just like, I don't understand what any of this represents, but cool. We're just going to copy this in our notes. So, I mean, it was in the context of history and like, um, how the in that particular case there were many of these. In that particular case, it was like how the religion of the area kind of demanded a certain psychological, uh, like necessitated a certain psychological profile of the people within that society, and therefore that's how this history came about. So this was mostly European, um, post well, right around Renaissance anyway, like pre and post Renaissance Europe. So talking about the grand cathedrals, especially Notre Dame and all this other stuff, the flying buttresses on the outside. So these uh, his name isms were very much instrumental in all of our like learning all this stuff. And at some point, he was trying to say that like society is almost like each individual society is almost like an entire organism. But he missed a syllable. And we being ninth graders, of course, just like, oh my god, did that just happen? This dude's like 60. I don't want to hear him talk about that. And he's got this. No, no, no. That's Boston. Uh, he's got a great New York, Long Island accent, so he's very Italian. It's tempered a little bit by his Boston accent as well, but mostly it's New York. So, the great human orgasm. We're like, oh God. uh, he was also, let's see, he also taught our senior level psychology class, which was pretty brilliant, but very weird because he decided as a textbook. Um, we were not required because he could not have copies of it. Copies of it were not allowed in the school. But it was a book that was like a graphic novel essentially about Sigmund Freud. And so there were like, just pages and pages of all sorts of really weird stuff because it's graphic novel about Sigmund Freud. Um, and it starts talking about like, all the stuff that's, um, yeah, that's biology class. You can get away with that. Um, but yeah, we were allowed to go to the private school bookstore, which was maybe like a mile up the street. And they had copies of this particular book in stock all the time. In fact, they had almost exactly one class's worth extra. Oh dear. So, like, he put in an order at their bookstore every year to have, 20 some odd copies of it just on standby, just in case. And so we, pretty much every one of us, because this is our senior year, so we're all, 18 or whatever. So we go down there and it's like, I don't know, 12, $15, something like that. Yeah, so like the private school has it, but we're not allowed to have it in our public school because it's too risque or something like that. It was there were pages that were bordering on pornographic because it's Sigmund Freud, and of course they're going to have pictures of naked people or whatever in it, and so somebody apparently put up a big stink, and he was not allowed to have a set in the school, but yeah, we were allowed to just go out and purchase our own. So I still have it. It's But yeah, it was kind of interesting. Um, I mean, after that, I had a lot of thoughts about Sigmund Freud, not the least of which somewhat tempered by um, Lieutenant Commander slash Commander Deanna Troi from Star Trek: The Next Generation, when she was just like, oh, God, why? So if you ever saw uh, Next Gen, and especially, you know, that one episode where Data decided to get analyzed from a third party AI system rather than his actual counselor. Star Trek: The Next Generation. So, um, so in Star Trek, yeah. So Star Trek: The Next Generation, they've got several people who are on the ship. I mean, obviously, but different, but also similar to the original series. So you had instead of Spock, Kirk, McCoy, etc., you had Captain Picard, who's much more, um, well, I mean, he's Patrick Stewart, but very Patrick Stewart. He's interested in theater and um, philosophy, and so he's very well read in terms of like that's his hobby is just he will read books about everything. And then you've got Lieutenant Commander Data, who is sort of the Spock stand-in, who is completely logical, being an android. So he will, be very focused on what is logical and what is true and what is all this, and he longs to become more human. And the McCoy stand-in actually comes in the second season when what's her name? Gates McFadden, who played the Doctor on the first season, got fired because she was making a fuss about how the women on the show were not being given, non-sexist parts. So she made a big fuss about it, and they're like, "Fine, leave." So eventually they were just like, "Okay, well, you're not leaving, so we don't want you around anymore. Goodbye." Which was a huge mistake on multiple fronts. Um, so they get this lady on who plays a much more technophobic, uh, android hostile doctor who is basically berating Data the same way that Dr. McCoy berates Spock. But when it comes across on the original series, it came across as like straight up racism. And when it comes across on Next Generation, it comes across as like she's just kind of hostile against Data because he's an android. So she treats him like a toaster. It's still not good, but at the same time, it's like slightly less bad. And then it starts coming off eventually as like sort of mean-spirited, because at some point the whole audience is just like, okay, fine, get over it. And she sort of does occasion or like eventually, but it's never really like hammered home that they're good now. It's so they've the Next Generation is an interesting continuation of the original series, but like the themes are the same, people are completely different, and they ended up having 7 seasons of this show, unlike the original series, which was on for I think 2. But they made such an impression that, like, over 2 seasons, that, 20 years later they came back for the movies. Well, 10 some odd years later. But yes, Counselor Deanna Troi is the ship's counselor and analyst, psychologist, all sorts of stuff like that. And she's supposed to be very super empathetic. Her entire race is telepathic, so they're mind linked. She's only half Betazoid and half human, so she kind of gets emotions rather than like straight up can read minds. Um, and so eventually, at some point, um, Commander Data starts having dreams, and so he's like, "I need to analyze these dreams." And he goes to the holodeck, which is basically giant fantasy room, and you can have whatever you want in there. So he replicates inside of this room a Sigmund Freud program, and he's like, "I need to discuss my dreams with you." And Sigmund Freud's the typical, stereotypical German Sigmund Freud, cigar smoking, lay on the couch and let's talk about it, psychologist, psychoanalyst, and starts talking about his father, and he goes, "But I don't have parents." And he's like, "Ah!" It's a really good scene, at the very least. If you look that up on YouTube, I'm sure it's there. But yeah, Deanna's like, "But why are you going to see Sigmund Freud? Like, you do realize I'm a counselor, right? Like," yeah, at some point he straight up goes Oedipal complex and suggests, this this knife you see in your dream. It's very much like the urge to kill your father, and then the fact that this thing, um, there was a cake in the shape of a person. And he's like, and your desire to eat your mother, and he goes, "But I have no parents." And he goes, "Ah, complexes upon complexes," and he's it gets somewhat ridiculous. It's almost as good as like the Hitchhiker's Guide version of Gag Hellfront, who's again supposed to be like Sigmund Freud's stand-in. Of course, he's only actually after money, but that's neither here nor there. Wonder if this is like a step function or something. If it like starts decreasing and then stays the same over at least a couple, or if it's like the primes, the prime count. Has that like approximately logarithmic curve to it. I just kind of wonder if it'd be interesting. I mean, I've got to be able to write a program. I'm in a trivia league today, or I'm in a trivia league, and they today for the online thing, one of them was there's a 2020 there's a 2020 documentary series done about this person, which has a meme that has come out of it, which is and so I took it personally, or something like that. even though he never actually says it, it's been memed as that because it was sort of the, the uh, sort of the context for how this person was feeling about something in particular. And so I didn't know what it was. But then I decided, okay, I'm going to get this question wrong on purpose, but now I just need to know who it is. So I got the question wrong on purpose. I look it up, and it was there was a Michael Jordan documentary done in 2020, and so I put down, um, so then I put down in my answer, "Stop it, get help," which is the other famous Michael Jordan meme. uh, but yeah, it's a fun time. Oh man, that was a anti-drug commercial, right? It's got to be. I can't even remember what the original was. Yeah. All right. I think we're probably gonna end it and send this off to somebody who's on tonight. Yep, JCM. Jason Charles Miller, as always. On tonight. Let's see what he's up to. All right, so thank you, Superbrain. Thank you, Two Curbs. Thank you for everybody who came on in and helped out with the awesomeness that has been here. Welcome again to Aphelium Panda. Thank you, Megalomorph, and yeah, now I can't remember who else. I'm sorry. We've purged the chat record at this point, so yeah. So anyway, thanks everybody for coming. This has been fun, and hope to see you on Friday for some more games. I found out that Trail of Ayash came out with another release or another update. So for whatever reason, mine just didn't work last week, but it was working for everybody else, apparently. But whatever. So I'll I'll try it again and see what happens. They suggested that I purge my save record, which I did, and then try it again. And like I said, last week it just kind of there was nothing there. There was no play button. So this week I have a play button. I'm gonna give it a shot. See what happens. Worst case scenario, we go play Valheim again because again that's the same kind of game. So with apologies to the devs again. All right, so here we go. Off in 10 seconds. So, again, thank you very much, everybody, for coming. This has been Obi-Wan Pez for N Simplex Pachinko. We will see you on